Good day, everybody. Today I'm here to demonstrate Newton's second law. Newton's second law is the law of motion that pertains to the behavior of objects for which all existing forces are not balanced. The second law states that the acceleration of an object is dependent upon two variables: the net force acting upon the object and the mass of the object. The acceleration of an object depends directly upon the net force acting upon the object and inversely upon the mass of the object. As the force acting upon an object is increased, the acceleration of the object is increased. As the mass of an object is increased, the acceleration of the object is decreased. Thus, we have force, which equals m times a, where F is the net force acting on the object, m is the mass of the object, and a is the acceleration of the object. The second law states that the net force of an object is equal to the rate of change, that is, the derivative, of its linear momentum, where P is an internal inertial reference frame. The second law can also be stated in terms of an object's acceleration. Since the law is valid only for constant mass systems, the mass can be taken outside the differentiation operator by the constant factor rule in differentiation. Thus, where F is the net force applied, m is the mass of the body, and a is the body's acceleration. Thus, the net force applied to a body produces a proportional acceleration. In other words, if a body is accelerating, then there is a force on it. In order to demonstrate this, I took a video of a roll of paper and just rolled it over a smooth surface in the balcony. There are my dogs in behind, so then I could actually see what the force that was produced and measured through the vectors exposed in the tracker video. Here we have plotted the tracing of the acceleration that was produced. Let's initiate the motion, in which we can clearly see in the x-y axis how the acceleration is going to take place, where F is the force net, which is going to be placed at this moment, and once there's a force acting over the solid, then it should move in the direction where the force was exerted. In this case, there's no significant friction, so the friction will not be accounted for it. Now the frames are going really slow. We actually programmed the program to actually plot the mass, which is the rate of acceleration at times t on the x-axis. Then we have the values of time, which we began at time t of 2.769, where we have a negative value of -375 and a y of 118 and an ending value of 6.539, a positive value of 303 in the x-axis, and a positive value of 271 in the y-axis. Here we can clearly measure and trace the distance, which was done with a vector, which shows exactly where the object actually stopped. And when we go and see the vectors, we can see a correlation between vector A at times t in the x-axis, which its value goes directly proportional, increasing from 0 to 1.74. And also we have the vector on the y-axis in which there's a decreasing force, which it begins with the force that it was exerted, and as the object moved towards its destination, actually the acceleration decreased. So we have an inverse proportional on the values of x and the values of y at times t. And here we can actually look at the values, which are all in the positive frame. If we take the x-axis and we turn it around, towards the negative values, then we can actually see that the values actually changed. Oh, they didn't. They didn't change. So the values actually remain the same, all positive values, but then the vectors change, where the value of x went on a descendant and the value of y actually stayed the same in its decreasing force. Now let's put it together again the original way, where the value of x is positive, and there we go, and we can see the inverse proportional where the vectors actually oppose as the value of x actually states that the oh, here we are with the negative values once we change, where the value of x at times t goes in decreasing and the value of y at times t goes increasing. Now let's change it again. There we go. Sorry. There we go. And now we can see the inverse proportional again, where the values here go back to positive. Now we took these values and then we plotted them into the Python program, and we're going to run the module, which was pretty successful, where we can see actually how's the movement that goes vertically up north, but then in our graph what we show, instead of increasing, we show a constant force in which the acceleration actually stayed the same. And that's it. We can see actually here the values in which the values of y, the magnitude increased as the time was lower, or lesser, and the magnitude decreased as the time got longer, to prove that once the force was produced at time zero, right here there was a greater magnitude which went decreasing as the distance went further from the point of initiation. And that's all for today. This is the explanation of Newton's second law. Thank you very much. My name is Lucia, and I'm reporting from Madrid, Spain. Have a great day, and I hope that I was able to explain the Newton's second law with the example that I provided through this video. Thank you, and have a great day.